Now consider this topic, 4 to 20 milliamp current transmission. Let me lay the context for this. We saw this application, right? We had a heater and we had the temperature being sensed of the heater, and this value of the temperature in the form of a voltage or a current was being transmitted as a feedback to the digital domain. So this, the first step in analog signal processing, from the output of the transducer, the electrical parameter, voltage or current, is first passed through a zero and span circuit. So this will adjust the offset and it will adjust the slope or the gain of the signal that is coming out of the transducer such that it is compatible with the downstream circuits, especially the A to D, so that the full range of the A to D can be utilized. So before you give to the A to D, you pass the signal through a anti-alias filter so that you band limit the signal so that there are no aliasing effects, so that we can reconstruct the entire signal in the digital domain. After that, passes through an A to D and into the digital domain. So this is how the signal from the transducer in the analog domain passes on to the digital domain. So this is what we saw. This is typically the case. These three blocks will be typically the case that you will see in most of the electronic systems. But there are some cases where this transducer is located at a remote end. It could be located at a place where the temperature is so high a human cannot go to that place, or other electronics can not work in its proximity. So therefore this can be placed at a remote place. So if I say that this transducer and then let us say along with the zero and the span is at one location, and the anti-alias, A to D and the digital domain and the controller and all other parts of the electronics, the control electronics is at another place or another building, then you can see that I can make a break here and say that this is at some distance, let's say 1 kilometer distance. So what is the effect if it is at such a great distance? Let me zoom this part. Let me zoom this part alone. So on that part, one end is zero and span. Let me write it down, and at the other end is the anti-alias part. So all the anti-alias and all this part, I'm going to put it as an equivalent load resistor, but it could also be the input impedance of whatever you see at the input of the anti-alias filter. This is equivalent load resistance. Now these two are connected through some long wire because you're talking a 1 kilometer distance. Let me make some space. So this side I'm equating it as a source because the transducer is now the source. Transducer along with the zero span circuit is going to give some voltage Vt. Okay, this voltage Vt. And on this side is the voltage Vr. Why did I give the subscript T and R? Voltage Vt at the transmission end, voltage Vr at the receiving end. So that's why in order to distinguish, I am giving Vt and Vr. Now is Vr going to be same as Vt? Even though this is copper, there is going to be a lot of resistance. There will be a lot of resistive drop distributed along the line. Vr is not going to be equal to Vt. So let me lump all the resistances in this loop. This is the forward path, and this is the return path for the current. So I will put the resistance. This is the R line. I am lumping it, and there is a current flowing through this loop. Now, VR is equal to Vt minus this drop I into R line. Because current I is going to go here, this is plus and minus. So Vt minus I into R line is available at Vr, is coming at Vr. So Vr depends on the current I apart from Vt. But this portion where it is dependent on I is the cause of the variability. So Vr, you are not fully sure, because depending upon the load resistance, I will vary, and therefore Vr will vary, and you won't know whether the Vr has varied due to variation in Vt, due to variation in the temperatures, or due to variation in I due to change in load. So this will not kind of be available, or that knowledge will not be known at the receiving end. Where that is where you take this voltage Vr and convert it into the digital domain, and there will be sufficient sufficient uncertainty and not good for the precision or the accuracy of the system. So therefore, whenever you are using this kind of a long distance long distance transmission of the data or the knowledge from one end, a value of the signal from one end to the other end, you need to convert this into a current source so that you are pushing current. So if you are pushing current, whatever may be the line loss, doesn't matter, it is the same current that is flowing through the receiving side load also, irrespective of the amount of the line loss. And that current is absolutely the same, whatever it is at the sending end and also at the receiving end. So the trick is convert this voltage source into a current source I, which is proportional to Vt. So voltage to conversion, current conversion you do, and then push this current along the long line into the other end, the receiving side, which is some load, let us say. So now Vr, now this is RL, let us say, and I will put this distributed line losses as a lumped line loss R line. And there is a current which is being pumped in, this current which is pumped in, this is I. Now what is Vr? Vr is nothing but this current which is being pumped in through into RL. I into RL. I is proportional to Vt because we used a voltage to current converter here at this side. So at the transmission side, so I is proportional to Vt, and therefore Vr is proportional to Vt into RL. So therefore you see that Vr is proportional only to Vt, and therefore the precision or the accuracy of the entire system is retained, maintained, even though there is a long transmission line coming into the picture. Long transmission line of the signal. So therefore at this point you need to interpose a current transmission system. So you have to interpose a set of electronics there, which will come analog, which is also part of the analog signal processing unit, which will transmit current and receive current through whatever the distance this may be. So we now, with this background, we now look at how we prepare the voltage that is available here at the end of the transducer. We convert it into a current, equivalent current value signal, transmit it over the long line, and on the receiving side, how do we receive the current, convert it back into the voltage, appropriate voltage. So this is what we need to see, the transmit and receive part of the current. Why 4 to 20 milliamps? That I will explain. But now the important takeaway is that you need to convert the voltages coming from the transducer and the zero span circuit into a current, equivalent current signal, transmit it over the long line to be received and converted back to voltage. So let me consider the transmission part first. So let me draw the circuit of that and explain its operation to you. Transmission part. So it consists of an op-amp in its very simplest form. It is just a non-inverting amplifier. I'm drawing this op-amp. You have VCC, VEE, plus and minus. I'm putting it in this fashion. Normally I put the plus below and minus towards the upper side. But note that I have put plus on the upper side and minus here just for convenience. And minus to ground, I use a resistor to ground that. And then from here you have the feedback loop. And this is the long line. Let's say 1 kilometer or longer line, let us say. There is R wire resistance, some load. It could be an anti-alias filter or whatever that load you see there. And here from the transducer you have a voltage which comes from the output of the transducer, and that voltage is passed through a zero span circuit to get VT. VT which is proportional to whatever the physical parameter that is being measured by the transducer. Now the operation is as simple as this. What does this do? So let's say this is plus. Now this is the voltage to current conversion circuit. I will call this resistor as R. This is the most critical component here. And because of the virtual connection, virtual short here, if this is VT, this is also going to be VT. I'll write this one, VT. And what is the current that is flowing here through this resistor? It is going to be VT divided by R. That is current I. So this is going to be the loop current. So this is the current that is flowing through here. It will flow through the load. It will flow out of the op-amp output. So the current flows in this fashion, goes through this load, through all the wire resistance, then flows through R into this. There is no current flowing in here because of the very high input impedance of the op-amp. So VT by R. So I is proportional to VT by this proportionality factor 1 by R, and I into the load resistance will be the final output. So it's the same current as decided by this R that is going to flow through the remote side load. So let us try to understand some salient points of this circuit. So one is R wire plus R load is the feedback voltage, what we would normally write as R2. Remember, in a non-inverting amplifier, if what is connected, the resistance that is connected between the output and V minus point is R2, and you say 1 plus R2 by R1 into V in is the output voltage. So R wire plus R load is equivalent to R2, and this impedance, whatever be the value of this, is not going to affect the value of the current that is going to flow. The value of the current that is going to flow is only decided by this component R, by VT, that is the input voltage, and R. So therefore it is immune to all these wire impedances. But what is V out? V naught is 1 plus R wire plus R load divided by R into VT. So this is V naught. So normally you don't need to bother about V naught. It is not going to affect the current that is flowing through the load. But you need to only bother about the extreme values. See that here VCC and VEE are there. So you have plus V and minus V actually, or plus VSAT and minus VSAT. V naught should not go and saturate. It not go and saturate at VCC, nor should it go and saturate at VEE. So you should keep that value low. You don't have much control in changing the value of R wire and R load, but you have control on R. Therefore, you can adjust R to see that this V naught is less than the saturation value or the supply voltage value. So by adjusting this. So this you need to keep in mind. Next, the op-amp must be capable of sourcing and sinking the current of value I. So the current of value I is decided by this resistance R and Vt. So this R is actually going to flow out of the op-amp if it is flowing in this direction, or if Vt is negative, you will see that the current will flow into the op-amp output. So op-amp should be capable of sourcing or sinking the current that you will decide with this value of R. That is important. So the sourcing and sinking capabilities, the maximum current I is generally governed by standards. So there are industry standards where it says that maximum value of the current I can be 20 milliamp or 60 milliamp. These are the industry standards. So in several cases, the op-amps may not be capable of sourcing and sinking 20 milliamps or sourcing and sinking definitely 60 milliamps. How do you then modify the circuit to address this problem? So let us do that. So let me make some more space here. Let me draw this op-amp. So I am just going to have an extended wire for VCC and VEE, and I will keep the remaining portion of the circuit same. This is the Vt, transmission side voltage. I have this resistance R and the long loop. So this is what was connected to the load. This is what was there, right? But our problem is that the current, this current I, which is decided by R, may or may not be possible to be delivered, sourced or synced by this op-amp output. So therefore you need to put some extra circuit. That's what I'm going to do. I'm going to do a current boost. So let's say that I have a BJT connected like this. This is to the V plus, and the base of the BJT connected here. So if I have this current I flowing through like this, in this fashion, so the current I is flowing through in this direction. So this is sourcing out. So the current I is flowing here. This current, the collector current or the emitter current is I. Then the base current is what? Base current is I by beta or I by HFE. The base current is I by HFE or I by beta of the BJT. So if the BJT is having a beta or HFE of 100, and if you are talking of 100, if you are talking of 60 milliamp current flowing by the 60 milliamp standard, max current of 60 milliamp, then divided by 100 would be 0.6 milliamps here. So 0.6 milliamp is what the op-amp has to source, which is possible by most op-amps. So this way, by adding current boost with appropriate beta or HFE, you will be able to boost the current to the industry standard values. Now if you are sinking current, that is if Vt is negative, you will see the current flow in this opposite direction, current flow opposite to this and then flows into the output. So you need to sync, you need to have similarly like the current boost you had here, a current boost for syncing. So use a PNP stage, order the current will flow through this to the negative power supply, and what flows here in is I by beta. So this is the current boosted voltage to current conversion. So this is what you need to use when you know that your op-amp is not able to deliver the required amount of sinking and sourcing currents. Another comment here is floating load. Because the ground is here and then the load is connected between these 2 points, it is floating. So it is a floating load topology. So one of the disadvantage of floating load topology is that you need 2 wires to go to the remote end. If you have 1 kilometer of 2 wires, one for forward flow of the current and another for the return of the current. So 2 wires are needed, 2 transmission wires. But you also have advantages. Because the current flows in one of the wire and returns the other wire, the signal is essentially differential, and because of the differential signal, common mode problems can be avoided. Next, the fourth point, open load and fault conditions. This is very, very important. What happens if the load is open? The load is open, I is 0. So if I is 0, the system, the op-amp is operating like in a comparator mode. There is no virtual ground. So the output will saturate to V plus or V minus. Keep that in mind. Because current here is 0 at that point in time. Under fault conditions also, if some fault, let's say that the transistor is gone bad, damaged, or the op-amp is damaged, there is no flow of the current, but the input transducer is working properly. Even then current I can be 0. Now this is a distinction that one has to make. So when the current I is 0, the remote end does not know. Should it take that the Vt value is 0, that is the transducer output is 0, or should it take that there is a fault condition that has happened due to some of the component which has gone bad. So the remote side load does not know that. It's not a unique condition. So there are 2 conditions which can give I is equal to 0 or remote side voltage is equal to 0. One is that you can have 0 transducer, 0 span circuit output voltage, or due to a fault or due to a damage in the component, I can be 0. So you need to distinguish this. So in order to distinguish this, what is employed is that there is a minimum current that has to always flow through this external load or the long loop. So that minimum current is defined as a standard, which is 4 milliamp. So 4 milliamps implies that Vt is 0. If Vt is 0, here 4 milliamps is supposed to flow. Vt is maximum, 20 milliamp is supposed to flow. So between that you have the range 4 to 20 milliamps current will flow. If current is 0, then the one and only condition that can happen is something has gone bad. Because Vt, when it goes to 0, 4 milliamps, the voltage, an offset voltage, 0 span circuit should come in, which will dictate an offset voltage where 4 milliamps will flow when Vt is equal to 0. I will show that in a moment. So, this important consideration has to be taken into account so that when Vt is 0, we want to have 4 milliamps to flow in the remote load, and when VT is max, 20 milliamps to flow. And when the remote load current becomes 0, then I know that this has gone bad. So this is the 4 to 20 milliamp standard. So that is how it has evolved. So now let me consider this portion to show you how we get 4 milliamps to 20 milliamps. How do you give the 0 and span for this VT? So let me consider this part of this whole circuit. So that is actually coming from a zero span circuit. So we saw that we have a transducer, let's say temperature transducer in this case. The temperature transducer is measuring the heater temperature, and that is being given to a zero span circuit. So this is the input of the zero span circuit. The output of the zero span circuit is connected to this point. So that's what I have done here. Connected to the plus point of the op amp of the transmitter side, and all else being same. Right? So you need to look at what is the transfer characteristic that you would like to have here. So if I am having the x and y axis, this temperature, what you have here, I will call it as Vi, input to the zero span circuit, and this is Vt, transmission side voltage, which will determine the current that flows here in this loop. So if your x-axis is Vi, y-axis is Vt, then I would like to have a transfer curve in this fashion as shown here. I'm going to have an offset. When Vi is equal to 0, I want Vt to have an offset. So that when Vi is equal to 0, Vt will be having an offset, and then from there on increases linearly till Vi max, where I will get max value of Vt. So now let us say if this is Vi max, that will be correspondingly Vt max. This is going to be Vt min for a 0 Vi. So why do we have this? When Vi is 0, we want some minimum current to flow through the output to indicate that it is 0 Vi. So when Vi is 0, Vt is at Vt minimum. This is that offset. So what is that value of offset? That offset gets translated to the node voltage here, and that divided by R will be Vt min by R, which is 4 milliamps. That will be the minimum current. So when Vi is 4, you can set R to have 4 milliamps flowing in this loop here. And when Vi is maximum, Vt is maximum, and therefore this will be Vt max at that point. Vt max by R will be 20 milliamps, let us say. So you have this entire swing of Vi from 0 to some Vi max will result in a swing of Vt minimum to Vt max, will result in a current loop of 4 milliamps to 20 milliamps current in the current loop. So this is how the 4 to 20 milliamp standard has come about implemented in this fashion using this transmission circuit. Very simple transmission circuit with current boost. Till now we have been looking at load that is floating. But how will the circuit topology look like if the ground at this end was grounded? So grounded with this being the circuit ground. So let us look at that topology also. That is also a common situation that will arise where the load at the remote side, at the receiving side, is grounded. So let me draw that circuit for grounded load. So grounded load topology also consists of the op amp. Now I will draw the op amp like I normally draw, with the plus at the bottom side, minus at the top side. We have VCC and VEE, don't forget the power supplies. So on the inverting side, with respect to the minus terminal, I am going to have this negative feedback set of resistors that you are normally used to seeing for an inverting amplifier. I also will have, for the positive input, an attenuator like this called the difference amplifier. The difference between this potential, superposition of this potential and this potential, will come upon at this point. That is the V plus point. So let me start completing the circuit and then I will explain its operation. So let me put two sources here. So V1 and V2. Then I will put a series resistance here. This is a very important resistance. This is the key element here. And further on the remote side, you will see that there is the load. So this is the one which goes to a long distance and reaches to the load, and the load at the remote end is also grounded, which means this point and this points are common. They are all connected to the common power supply grounds. Now this end, I will make a connection in this fashion. So this end I am going to make a connection to here. So this is the difference. This is the different thing about the non-inverting part of the amplifier. This is the inverting part of the amplifier. This is the non-inverting part of the amplifier. So this connection is the one which will convert it into a constant current or a voltage to current conversion apparatus. So let us mark some variables. So this is the current that is going to flow to the load. I will call it as I. And here we will call it as VL, voltage across the load. This is V0, output voltage of the op amp. This is RS, the series resistance. This is V1 and V2. R1, R2, R3, R4. Okay. So let us consider R1, R2, R3, R4 or R all as equal to R equal. It will make life simple, but I will use the subscripts R1, R2, R3 in the equation to indicate which resistance that we are aiming at. So V0, what is this V0? So this V0 is coming from all these 3 points, V1, V2 voltage and VL voltage. All these are going to superpose accordingly and you are going to get the output. So let me superpose them. First V1, first I will take V2. V2 and VL, this is VL, are going to get superposed at this point. So I will say V2 into R4 by R1, R2 plus R4, R4 by R2 plus R4 plus VL, this is VL at this point, R2 by R2 plus R4. So this is the voltage that is available at V plus, and that is multiplied by this gain 1 plus R3 by R1. because V naught is equal to whatever the voltage drop across R3 plus V plus voltage, which is that. So that's why 1 plus R3 by R1. Then minus, there is V1 component which comes to the output because that is going as an inverting amplifier, V1 into R3 by R1. So this would be the voltage equation. But let us apply this constraint. Let's say R1 is equal to R2 is equal to R3 is equal to R4 is equal to R. Then this will become V2 by 2, VL by 2, and this will be 2. So therefore V2 plus VL, here R and R will cancel, minus V1. So it is VL plus V2 minus V1, that is V naught. Now what is the voltage across RS? What is the voltage across RS? VRS. VRS is this voltage V naught minus VL. So VRS is equal to V naught minus VL. But what is V naught? V naught is VL plus V2 minus V1 minus this VL. These two will cancel. So you will have V2 minus Vn. So this is the key relation. So what is the current through IRS? It's IRS, right? IRS is equal to V2 minus V1 divided by RS. So this is the current that is flowing through RS. So it can branch off this side and it can branch to the load side. But let us say that I want to make this current 0. How do I make it 0? I will buffer this one. So what I just need to have the voltage value here, VL voltage value, so I will buffer it. So what I will do, I will make some space, I will put a buffer, supply, and connect it in this fashion, right? So whatever VL is there, this is VL, and then this will also be VL point. So the current here, which is I, the current here will be I, the same current as here, because this current is going to be 0. So you see that this is the key component which determines the current. So this I is equal to the I, which is IRS, and that is purely the difference between V2 and V1 at the input voltages divided by RS. RS is our design resistor. RS is the series resistance, is our designed resistor on the transmission side, and the load side current will be exactly same as what is determined by the voltage drop of this divided by RS. So if you make V1 is equal to 0, then IRS or I will be V2 by RS, and if V2 is coming from the output of the transducer and the zero span output, then I will be proportional to V2. If you want to give an offset, for example, you want to give a current here of 4 milliamps when V2 is 0, you can use this as your zeroing circuit or offset adjust circuit. So you could have a negative value of voltage here, and see that because this will again invert because of the minus sign, you will get a positive voltage drop across this when V2 is equal to 0, and by RS we can set it to 4 milliamps. So 4 milliamps to 20 milliamps can be then from V2, which can vary from 0 to some maximum value. According to that maximum value, you can tune the other values of resistors R such a way that you get 20 milliamps as the max value. So 4 to 20 milliamp is possible even in this topology. So till now we were looking at the transmission side circuit. So we now go to the load side here and look at how we will receive this signal and then reconvert it back to compatible form so that ADC can take it, the anti-alias filter, and ADC can directly use that to convert them ultimately to the digital domain. So let us look at this part, the load part. So this is the floating load. We will look at the floating load, and as an extension, the load that is grounded is the easier part, and then we can look at that also. So let me make some space and then write the receiver. Receiver circuit. Okay, so we are getting from the remote transmitter, from the transducer, quite some distance, we are getting the signal where the current I is flowing. We will terminate here with a resistance. So let me call that resistance as RL, and the current I that we obtained, designed this value of I to flow 4 milliamps to 20 milliamps. 4 milliamps when the transmission side voltage is 0, and 20 milliamps when the transmission side voltage is maximum. So I flows through this, and there is a drop across this I into RL. So this is the voltage that we need to process. So let me process it using an op-amp. So in the op-amp, I'm going to write it plus minus. You would have studied the differential amplifier or the difference amplifier, which gives the difference between the two voltage sources at the plus and the minus side. So let me draw the topology of a difference amplifier, which is very similar to the non-inverting amplifier and inverting amplifier both put together. So there is a voltage divider at the non-inverting end. At the inverting end, you have the regular resistors at the minus input and the feedback resistor combination. So here are the two voltages that would be given, and the difference between these two voltages. So if this is V1 and this is V2, V1 minus V2 is what will appear here if all the resistances are equal. But I want to find the difference which is across this resistor IRL. Now it is positive here as the current is flowing. So this is the plus point, right? This is the minus point. So the plus point, I am going to connect it here, and the minus side I will connect it here. So the difference across these two IRL is what will appear across here proportionally. So now I will make all the resistances R and output V0. So what is V0? So if I take the plus side here and the minus side here, it is IRL difference. This IRL directly comes to the output because all these are same value resistances. There is no gain. So output is equal to I into RL. So this is the regular difference amplifier. Now I will use one more op amp, plus and minus in this fashion, VCC and VEE. And here I will have a potentiometer. This is plus V plus and this is V minus, and tap a point and buffer it. So which means I can adjust the tap here and get from plus V to minus V, any voltage I can get from this tap. And I will buffer it and give it here at this point. So this is going to be our V offset. So I will remove that ground and then connect it in this fashion. so that the voltage here will be superposition of this voltage and this voltage, V off and this voltage. So the output will also have a offset component. Whatever this V0 will be whatever this voltage plus this offset component which will come here. So the offset component, if I divide it by 2, because it's a superposition value, R divided by R plus R, and into 1 plus R by R, which is into 2, so which will come as a offset component. Okay, so this is the concept so that I can manipulate offset, and I can also manipulate the gain of this to get the zero and span adjust. So now these are not buffered. These are directly given to this point. We need to buffer them. So you need to put a topology here corresponding to the instrumentation amplifier topology using op amps. So let us use that topology. So let me copy this here and make some space, and I will make a cut here, okay, and I will push this, make some space there. So here I will include the instrumentation amplifier topology so that these 2 points can be buffered so that they don't get loaded, and you will get precise and accurate results. So I will have 2 op amps in this fashion, VCC and VEE, VCC and VEE. Now note the polarities carefully, plus here on the top side, minus, and here minus on the top side, plus the bottom side. Okay, very important. So the plus I am going to give it to this in buffer mode, and the minus I will give it to here again in buffer mode. So high input impedance mode, so there is no loading on this at all. So absolutely almost zero current flows through here, and I will have 3 resistances connected in this fashion, and the negative or the minus terminals I will connect to this point, and this minus terminal I will connect to this point as indicated by the arrow cursor. So this is the connection that I would make. So this is a high input impedance instrumentation amplifier topology, which will give you a difference of this across this with a gain. So let me illustrate. So I will call this as RG. This is the hero here, RG. I'll make this R, same as this value R. So this R, R, this R and this R are same, equal. RG is the only one which is different. So as this is plus and this is the minus, the difference here will be plus minus on this side. Let me indicate that this is plus and this is minus, and the magnitude will be I into RL, whatever this is, I into RL. The reason is that whatever this potential, virtual ground, and that potential is coming at this point, right? And whatever this potential through this virtual ground, it comes at this point. So this 2 points are the difference potential, which is exactly same as this, which is IRL. So that is IRL with the sign shown here. So which means IRL divided by RG, there is a current which is going to flow up like that. Okay, it is going to flow up like that. IRL divided by RG. And there is going to be a drop RG plus 2R. There's the current IRL by RG will create a drop across all these 3 resistance, so that you get a drop from here to here as IRL by RG into the sum of all this resistance RG plus R plus R, or RG plus 2R. So that will be the difference voltage which will get presented to this difference amplifier. So let me make the connection. So I will make this connection here and this connection here, right? And we will rewrite the output equation. Output equation is IRL divided by RG is the current. The current is flowing up. So plus and minus here would be into RG plus 2 times R. There are 2 R's, R plus R. So this is the difference portion which comes out, and there is the offset portion, V offset divided by R, because you have the superposition happening at this point, into 2, so plus V offset. So this is the output voltage V0. I will just rewrite it. V0 is equal to IRL into 1 plus 2R by RG plus V offset. This is the final relationship on the receiver side. So if I take the input output relationship, where I take, this is the transmission side voltage on the remote side, transmission side voltage, and this current I. Okay, we know that it is between 4 milliamps and 20 milliamps. So the current here is about 4 milliamps to 20 milliamps. 4 milliamps when VT is 0, and 20 milliamps when VT is maximum. So the relationship VT to I was like this. So at this point, so let me copy and place it here. So at this point, so here if you look at this one, when you multiply it by IRL, so I will multiply it by RL. Multiply it by RL, the relationship becomes in this fashion. So 4 milliamps to RL into RL will be here. 20 milliamps into RL will be a slightly higher jump. So the relationship between VT and IRL is this green line. Okay. So this IRL is further passed through this gain block, and then through a difference amplifier to the output. So you also have the offset point. So if I look at this, I can play with R and RG to adjust gain. So RG can be used to do the gain adjust or the span adjust, as we say. The slope can be adjusted. Then offset, which is coming from here, which can be adjusted using the tap here on the potentiometer here. You can do the offset adjust, the value here can be adjusted, and therefore you can get an offset adjust such that I can push this down to 0 if needed. So V0 here can be made to take this form of relationship, the red line, from 0 to some value, and this could be the VT versus V0 line ultimately on the receiving side, and this is what can go to the anti-alias filter, Sallen-Key filter, and from the output of the Sallen-Key filter can go to the A to D and into the digital domain. So this is for a floating load that we discussed. However, in the case where the load is grounded, this point will be grounded, the minus point here, and likewise this ground will carry on up to this op-amp input. So this point will be at 0 potential, and the difference will still be IRL between this point and this ground point. It will still be I into RL. So I into RL is what will get reflected here too, and all these will remain the same. The only change is that this point will get grounded, and this input of the instrumentation amplifier topology will also be at ground potential. Otherwise, all else remains the same. So this way you will see the entire entire block of circuits from the sensor to the A to D. So if you take from the sensor point, from the sensor transducer, the transducer output voltage or current is converted to a compatible voltage range using zero and span circuits. We studied that one. Then the zero and span circuit, if the transducer is in a remote location, you need to transmit using a 4 to 20 milliamp transmitter receiver combination, which we recently discussed. And then the output of that should go through a anti-alias filter so that you band limit the signals. After band limiting the signals, then you pass it to the input of the ADC and sample it such that the sampling frequency is greater than twice the band limit. Then you will be able to construct the signal back again in the digital domain. So all this form the analog signal processing block of our electronic system bird's eye view block diagram. You saw that, right? The ASP, the analog signal processing. All this form the analog signal processing block.